Okay, so we're space students. Here's lecture number 2, hopefully a little bit shorter on the sun. And we're looking at that image that I left you with last time. And I think to go back to this one to make a good comparison of the size of the sun to the planets, that's a good image to have. And of course, then if you take our sun compared to other stars, there's a big one. But look at our sun there. And you look at our sun, it would be less than a pixel, can't even see it compared to some other stars. Obviously, the sun is not the biggest star in the neighborhood, but it is a significant one. As I mentioned, it's 93 million miles from Earth, and that equals 1 astronomical unit. 865,000 miles in diameter, and it's big. It's not just sitting there, folks. It's spinning itself very slowly, about 4 kilometers per hour. And it's moving sort of to the northwest. If you can look to the northwest, that's the way the sun is spinning, counterclockwise, like the rest of the planets. And the sun is also orbiting around the center of our galaxy while it's slowly spinning, while we're orbiting it. And just to add another level of complexity to it, it is also flying out from the center of the universe while it's orbiting the center of our galaxy, while it's slowly spinning, while we are slowly orbiting around the sun, while we are ourselves spinning as we're orbiting. That should give you a headache. Okay, so what causes the sun to have so much energy, give off energy? Well, it's fusion. Let's see if I can shrink that just a hair bit. So here is an illustration of the process of fusion. Fusion, to fuse atoms together. And basically in the sun, light atoms, these are hydrogens, very light, very small atoms. 4 of them follow 2 different pathways. So 2 here. This is a positron, kind of the light side of an electron, if you will. It's a positively charged, similarly sized subatomic particle to an electron. We don't talk about them much, but they exist. They're another subatomic particle. This is a neutrino. Okay, so as these 2 fuse, those 2 subatomic particles are given off, and we've got these 2, this proton and this neutron, that are sort of a heavy hydrogen, have combined, and the same on this side. Another hydrogen comes along, and a gamma ray is given off. That's some radiation, a form of radiation, if you will. Okay, and so when that happens, now we have a light helium. We have 2 protons and 1 neutron. Okay, and the same on this side. When this light helium and this light helium combine together, they both lose a hydrogen atom, and we have a formal helium atom. So that there has been fusion, and energy is given off. This is the gold standard for nuclear power generation. Right now, we produce nuclear power by fission. We split atoms to make that energy release. But if we could do it with fusion, fusing light atoms together, we can generate more power, and the waste material from the fusion process is water. So really, that's what people are really searching for right now. So my question to you is the fact that, well, see, if you look in your notes, let's see, where do I have it? Yeah, if you look in your notes, it's in your notes. I want to make sure. You have that the sun currently, it is believed, has somewhere around 92% hydrogen and about 7% helium. That leaves 1% of other stuff, heavier atoms. Is that a good thing or a bad thing? Well, if you think about it, it's kind of a good thing. Because if you flip those hydrogen-helium percentage numbers, so if we had 92% helium and only 7% hydrogen, what that means is our sun would be running out of fuel, going dark, going dim, bad day for us. So it should make you really happy that there is a lot of hydrogen left, so that our sun has lots of fuel to make helium and make your voice talk. You ever suck in some helium from a balloon? I'm sure it causes cancer. But yeah, and your voice gets really high. I should have some here to do that. Anyway, that's the stuff. That it's a good thing that our sun has lots of hydrogen left and not so much helium. It'll burn for a long time. Okay, so then if we look at our sun and we look at some parts that make it up, It's not a complex structure in a certain regard, in that it doesn't have a lot of complex layers like the Earth does. But there are some specific ones that we want to pay attention to. It has a corona, it has a chromosphere, it has a photosphere, and it has a core. Okay. And if you look at that image of the sun's surface, and this is kind of a still image of just a boiling, seething cauldron of gaseous material. It would not be a very nice place to be. And here's another artist's rendition of the sun. I think that's an artist's rendition, although it looks a lot like an actual image. It's a little bit hard to tell because our satellites that take images of the sun have to process them so we can actually see them. And in that processing, it can make them look like an artist's rendition when they're really not. So I'm not actually sure on this one. So we're going to start off with a little video clip here, if I can pull that back up since my computer crashed. Oops, I guess I got it. Yep, there we go. So I'm going to pull this up. Actually, I'm going to pause the recording while I do that and get it set to the right spot. Okay, this is a video. It's got some good images. That's why I've chosen it. And it's got some images of some of the layers that we'll be talking about. So here we go. Okay, I want to back up here just a little bit. If I can find it. That one. Oh, shucks. That's a good image. Since we're talking, the first item in your notes under the sun's layers is the corona. That's a good image to have of the corona. What's this black spot? That's not the sun. It's not the earth. It's the moon. Okay, during a solar eclipse, it's the moon that actually blocks sunlight from reaching Earth. So in this particular case, we'll talk about different types, because sometimes the moon is a little farther from the sun and sometimes it's just a little closer to the sun. Sometimes it covers the sun completely and sometimes not quite completely. Call that an annular eclipse. Here it's covering completely, and that allows us to see the corona. We wouldn't see it otherwise. And so that's kind of a nice image to have. So I'm just going to drop this one down. Get rid of these files. Go back to that one. So if you look in your notes, the corona is that outermost layer of the sun. And I'm going to back this up just a little bit to this previous one. It's kind of a nice picture of the layers. And again, these are just layers of gases of different densities. And the corona is that outer layer, just very, very sparse number of atoms in it. The chromosphere would be like most of the atmosphere of the sun. The photosphere would be like the surface of the sun, so that the density of that photosphere is just a little bit greater than the chromosphere. And then you got the core. The video said that the core had 15 million degrees. I think it might have been Kelvin. My notes say 27 million degrees Fahrenheit. Don't worry about the temperature. It's hot, okay? We can't know exactly. That's modeling that would create those estimates of the temperatures. But those 4 layers are the ones that I want you to know. And the core is the hottest spot of them. And fusion is the process where hydrogens are fused into helium that creates the energy that we feel even on a cold day, winter day like we have right now. Actually, it's still fall, I guess. When you go outside, you can still feel that warmth from the sun. It's from those reactions. Just do that when you go outside. Just feel that sun's energy. That's energy coming from 93 million miles away. Good thing we're not closer. Okay, a couple of other things. Flares and prominences is the next thing in your notes. And this would be an example of flare or prominence. It's when there are storms or explosions on the sun's surface. And they can be spectacular. And if we look closely at a large one, right there's a large flare. This would be called an X-class flare. Actually, it has another name. It's called a coronal mass ejection. That's when the explosion on the sun's surface is so great that it actually blows sun's material out of the corona, that outermost layer, and out into space. I've got another image here of a coronal mass ejection. Right here, these are flares and prominences, but this is a big coronal mass ejection. Boom, it's blowing material, and we're protected here. So here's Earth, and these would be the radiation belt, the electron flow that creates our magnetic field, our shield, if you will, so that not too much solar energy gets through to Earth's surface, just enough to support life, but not so much that it would eliminate life because of excessive radiation or heat. Again, we're just the right distance from a star that's just the right size, that produces just the right amount of energy. It's got to be total fluke, no doubt. Our position is miraculous. But on occasion, big events occur. In 1859, there was an event called the Carrington event. It was a coronal mass ejection that hit Earth. Now, at that time, we had just developed, oh gosh, now the name of it is telegraph, and some electrification. Telegraph, main thing, is what we had developed. The Carrington event was such a large burst of energy that it actually squished Earth's magnetic field and blasted some energy through to Earth's surface, to the point that it melted electric telegraph lines. It caused fires all over Earth. People sending a telegraph message would get a shock when that hit Earth. Others disconnected their telegraph machines so as to save it. They were still able to send a signal even with it disconnected because there was so much current passing it made that contact possible. Absolutely incredible event. Yeah, so are they common? Well, coronal mass, now the sun goes through a cycle where it has lots of energetic transmission and then times when it's relatively quiet, quiescent, we would call it. During those quiet times, there's about 1 coronal mass ejection every 5 days. During the times when the sun is very active, there are coronal mass ejections, 3 per day, maybe more than that. So they happen a lot. But remember, the issue here is that the Earth is moving on a 586 million mile path around the sun. What are the odds that that coronal mass ejection would blow material away from the sun oriented towards Earth? Well, it happened in 1859. We have about a 12% chance every, every 100 years of, I'm not sure, I shouldn't say that. There is a significant chance that one could hit us. I think it was July of 2012. A Carrington event class coronal mass ejection. In other words, these coronal mass ejections, there can be little ones, there can be big ones. The Carrington event in 1859 was a huge one, biggest anybody had ever seen. One of those occurred in 2012, I think it was, end of July of 2012. It missed Earth by, I think it was 5 days in its orbital path. In other words, if it was pointed like this, Earth was just 5 days farther along its orbital path. If that had hit Earth, just think about what that would do to Earth. And I just want you to pause and think about, well, so what? Well, the so what is when a smaller one did hit Earth in 1989, it knocked out an entire power grid in northeastern United States and southeastern Canada. Communications would be interrupted dramatically, could damage satellites. The possibilities are a fairly lengthy list. It could be a big deal. It will be a big deal because it will probably happen again in our lifetimes. We just missed that last one. Boy, what's going to happen when the next one hits us? So that's a coronal mass ejection or an X-class flare, other name for the same thing. And, you know, if that happened here on this side portion of the sun and went down that way, it would miss Earth. And so it has to be oriented towards Earth's orbital path, and it has to be oriented towards the part of Earth's orbital path that Earth exists on or will exist on. Because it might take 4 days for that energy to reach Earth. Remember, Earth is 93 million miles away. That energy leaves the sun, it's probably going 1 million miles an hour. But to cover 93 million miles, and you're going 1 million miles an hour, that's almost 4 days to get to us. So it's got to lead us a little bit, if you will. And yet it is a real risk, and that can happen. Not to scare you too much. God's in control. So flares of prominence, bursts of energy from the sun's surface. The last item, I guess I got 2 more. Sunspots. When was it? There was an event called the Maunder Minimum. And let me back up just a little bit. If we have lots of solar energy going from the sun, it can hit Earth's surface. Oh, that's not the one I wanted. And when it hits Earth's surface, that's still not the one I wanted. Sorry, guys. There we go. And it can create auroras. Okay, the northern lights, or if you're down south, the southern lights. I'm wondering how many of you have actually seen them. I've asked this of the last several classes, and few, if any, have seen them. Well, part of the reason for that may be that we're at a quiet phase in the sun's cycle right now. Have you noticed the falls recently have been particularly nasty? We had winter from the middle of October. Yeah, we had some mild periods, but generally it's been kind of cold. Springs have been very cold and very, very cold, long into the spring as well. Farmers have complained about that. We've had some late June and Julys that have been ridiculously humid and hot, and then it went back to normal and then cold. So right now we're at a spot that is particularly you don't see many sunspots. You don't see northern lights. That's because the sun isn't kicking out a lot of energy right now, and so it'll change again shortly, and you'll see more sun. Well, you won't see sunspots unless you look for them, but you'll see potentially more northern lights. The farther north you go, the better your chance of seeing them. Some of these big coronal mass ejections can cause northern lights way south. I remember my brother-in-law was farming in western Kansas about 15 years ago, and he calls me up and says, "What you doing up there?" And he could see northern lights in Kansas. That's incredibly rare. He'd never seen them. Well, we'd had a coronal mass ejection, a smaller one, but it caused those northern lights. Well, sunspots then are, if coronal mass ejections, flares, and prominences are places where there's lots of energy coming from the sun's surface, then sunspots, these dark areas on the sun's surface, are what results from them. So this is where a coronal mass ejection, a flare of prominence originated from. Boom, and then once it's done, what it leaves behind is a sunspot, a dark, a relatively cool, you still wouldn't want to touch it, but cooler than the rest of the sun. And so, yeah, those are sunspots. If we look closely at one, geez, it looks kind of like, remember Lord of the Rings? What's the that eye? Sauron's eye, remember? You know, kind of looks like that. But when you see lots of sunspots, that means there's been lots of flares and prominences, lots of energy coming from the sun, which means it should be warmer on Earth. If you don't see many sunspots, then not so much energy coming from the sun and not so much warmth on Earth. And so if you look at the sunspot cycle, as was mentioned in the video, here's the sunspot cycle and here's temperature, okay? And some people feel that CO2 is not the driver of our current warmness. It's actually lagging behind. It's a result of changes in things like the sun, and that's what this attempts to illustrate. Okay, and there's northern lights. So, sunspots. I wanted to mention one other thing, and I'm going to try to play a video clip right now. I'm not sure it might block me for doing this, but I'm going to do it anyway. Because I love how Hollywood can take some astronomical events and use them. So let's just watch this little clip from Pirates of the Caribbean at World's End. Okay. Well, green flash. Now, I don't think it signals when a soul comes back to this world from the dead, but it is an actual astronomical event. At sunset, in southerly climates like the Caribbean, there can occur, if the horizon and the atmosphere are just right, this little bit of green, almost an aurora-like green above the sun's surface, just for a brief moment, a few seconds at sunset, just like they describe in the video. Good job, Pirates of the Caribbean, insofar as describing the event. Again, I don't know if they're going to block me for doing that. I might have to go back and edit this video. I'll worry about that when it comes. So, sunspots, green flash, a couple of last items. If you look at a comet, and we'll talk about comets again later, but I had mentioned that energy that comes from the sun takes 4 days, or it can get here as fast as 13 hours, but 4 days is kind of an average. Okay, so if you look at this comet, I'm going to try to link those two concepts together. If you look at this comet, so here's the comet, here's its tail, and I asked you what's causing the comet to have a tail. I'm guessing that you would tell me that it's its motion blazing through space, and this trail is kind of like a contrail from a jet. This is the remnants that are left behind as it zooms through space. In reality, that's not what's going on. and again, we will come back to this, that tail of the comet is created by the solar wind. This tail is created not because of the comet's motion, but because of the sun blowing energy out in space and blowing pieces of that comet behind it. Here's an illustration that I hope makes that point. So in a comet's normal path around the sun, it would look like this. It would not have a tail, just these round features. But as it gets closest to the sun, you know, this tail might make a little sense because it's moving this way, okay? Moving counterclockwise around the sun like it should. So this one right here might make a little sense because it looks like it's moving that direction. The tail's going that way. It's only off by a little. But you get here, and this is what the comet looks like. Notice there's two parts to the tail. We'll talk a little bit about that when we get to comets. But here's the solar energy, boom, coming away from the sun, and it's hitting that comet, and it's creating the tail. Same here, boom, away from the sun, hitting the comet, creating the tail. So that tail in a comet is not created by the movement of the comet. It's created by what we call the solar wind. That massive movement of energy away from the sun as it's being created by fusion. Solar wind. And then lastly, the solar eclipse. And as I mentioned before, this occurs when the sun blocks, or the moon blocks the sunlight from reaching the earth. And we'll distinguish it from a lunar eclipse a little bit in another one. But here's where I would stop the video and have you, or would stop lecture, and we'd make what we call the pinhole viewer, which is an activity you can do in an elementary classroom. And I will, hopefully we'll do that in class next Tuesday, and sort of pick it up from there. So I will stop there, and thank you, and you have a good day.